Here it is, guys, the last section of the semester. Okay, we're going to talk about Taylor and Maclaurin series. So in section 9, we were able to start with this standard geometric series and use several different kinds of tricks to find power series for lots of functions, right? We sometimes substituted different things in for x, or manipulated stuff around, or took derivatives or integrals, right? But it was all based on kind of just hoping we could come up with the right idea. And we certainly couldn't find power series for functions that are totally unlike 1 over 1 minus x, right? This has no hope of giving us a power series for cosine of x. So it would be good to have some sort of systematic way to find a power series representation for any function we're interested in, cosine x, or e to the x, or natural log of x, or anything, not just things based on the geometric series. So that's what we're going to do in this section. We're going to find a way to systematically figure out a power series for any function. Just as a side note, why do we want power series for functions in general? It's useful. It's useful to know a power series for lots of reasons. Some of them are, well, you can approximate values of the function very easily and very well. You can, right, and in fact this is what calculators and computers and so on do. If you ask it what cosine of 0.7284 is, the calculator will plug 0.7284 into its power series formula for cosine of x and go out enough places in the power series, enough terms in the power series to approximate that within, 10 decimal places or whatever you ask it for, however many decimal places the computer or calculator is looking for. Right, so you can approximate values of the function. And in general, the function itself, the whole function, you can think of as approximated by polynomials, right? If you take a power series, it's just kind of an infinitely long polynomial. So if you chop it off after the x to the 10th term or the x to the 100th term or something like that, you've got a polynomial, and that's an approximation for your function. And polynomials are great. They're really easy to work with, very easy to multiply, add, subtract, divide, integrate, differentiate, and so on. Or you can use the whole power series, and even that whole power series is very easy to differentiate and integrate. So you can find integrals of functions that you couldn't figure out the integral of other ways if you just use a power series and then integrate it term by term. So power series are really useful, especially for computational things. So we have a function, f of x. We'd like a way to figure out a way to write it as f of x equals a number plus a number times x plus a number times x squared plus a number times x cubed, and so on. A power series centered at 0. The c0 is the coefficient of the x to the 0 term, c1 is the coefficient of the x to the 1 term, and so on. This is our notation. But we need to figure out what those c's are, the coefficients. C0, C1, C2, C3, and so on. We're going to do that just by assuming we have this power series and plugging in 0 into it and its derivatives. So here's our power series. And what happens if we take f of 0, that is, plug in x equals 0? Well, we will get c0 plus c1 times 0 plus c2 times 0 plus c3 times 0, and so on. All of the terms with x's in them will disappear, and we'll just be left with that first number, c subscript 0. That means the number c subscript 0, that coefficient, is exactly what f of 0 is. So we're looking to find what c0, c1, c2, and etc. are. We just found c0. Okay, how can we find c1? Well, first take the derivative of our function, and take the derivative of the power series. Right? The constant term, c0, goes away. The c1x term, we take the derivative and the x disappears and it's just c1. The x squared term, the derivative of x squared is 2x, so the derivative of c2x squared is 2c2x. And so on. The derivative of c3x cubed is 3c3x squared, and so on. Now we plug in 0 again. F prime of 0, and again we just get the constant term of that, which is now c1. So that tells us that the coefficient c subscript 1 is just whatever number the first derivative of the function is when you plug in 0. So now you get the idea. We take the second derivative. The second derivative of f is the second derivative of the power series, which is just 2 times c2 plus 3 times 2 times c3 times x plus a bunch more stuff. All of the stuff represented by the dot 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 is things with powers of x that are x squared and above. So when we plug in x equals 0, we're going to get f double prime of 0 on the left, and on the right we just get 2 times c2 because everything else has an x in it, and so it disappears. That means the number c2 is the second derivative of f, plug in 0, and then divide by 2. Look at the third derivative. Now notice that at some point we stop writing lots and lots of apostrophes to indicate derivatives because it becomes annoying to count that many, and we just put the number of derivatives in parentheses. So f with a 3 in parentheses doesn't mean f cubed, it means the third derivative of f. So we take another derivative on the right, and we have 3 times 2 times c3 plus a bunch of things with x's in them. Plug in 0, divide by 3 times 2, and we get that c3 is the third derivative, plug in 0, and divide by 3 times 2. Now I want to point out, I'm just going to rewrite these slightly to make them look a little better. So I can, instead of f prime of 0, I can write f prime of 0 divided by 1. That seems silly. Instead of f double prime of 0 over 2, I'm going to write f prime of 0 over 2 times 1. And then that third one we'll write as over 3 times 2 times 1. And so you see that what we're getting in the denominator are factorials. There's 1 factorial, there's 2 factorial, there's 3 factorial. So now let's jump ahead and see what would happen if we did this for the nth derivative, right? The 19th derivative or something. What's going to happen to the nth derivative of our function? Well, all the terms up through the original x to the n term become constants and then disappear in all that derivative taking. What was originally cn x to the n, we take one derivative and that n comes down and then the new power is n minus 1. The next derivative, the n minus 1, comes down and the new power is x minus 2, and so on and so on and so on. So after n derivatives, we have n times n minus 1 times n minus 2, and so on, all the way down to 2, times that coefficient cn, and there's no more x's left. And then there's a bunch more terms, but all those terms have x's in them. So when I plug in x equals 0, I just get that n times n minus 1 times n minus 2 dot 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 down to times 2 times 1, that's n factorial, times cn. And that means the coefficient cn is the nth derivative of f with 0 plugged in, and that number divided by n factorial. So what did we just find? Assuming f has a power series representation at all, centered at 0, it has to look like this. That's what a power series representation looks like. And we have just figured out what the coefficients are. Each one is some derivative, plug in 0, divide by a factorial. And when we're looking for C0, we interpret that the 0th derivative to just be the original function, and 0 factorial, although it seems strange, is defined to be 1. So C0 is just the original f of function with 0 plugged in. C0 is f of 0. So as long as that power series is convergent, right, on the interval of convergence, we can write this function. F of x equals this power series. C0 is f of 0, C1 is f prime of 0 over 1 factorial times x, then f double prime of 0 over 2 factorial times x squared, and so on and so on and so on, and we get a power series centered at 0. That power series is called the Maclaurin series of the function, and it becomes very important in a lot of areas of math and physics. So there's the definition of the Maclaurin series of the function. We can generalize this. Instead of centering our power series at 0, we could center it anywhere. So center at x equals a instead of x equals 0. We can use the same ideas, follow the same procedure, just plug in some x equals a's instead of x equals 0. And we get, on the interval of convergence, the function is equal to this power series centered at x equals a. The same sort of formula for coefficients, only instead of plugging in 0, we're plugging in a. So it looks like f of a plus f prime of a over 1 times x minus a plus f double prime of a over 2 factorial times x minus a squared, and so on. That power series centered at a is called the Taylor series instead of Maclaurin series, the Taylor series of the function centered at a. And I just want to point out, if you plug in a equals 0, right, this turns exactly into the Maclaurin series. So a Maclaurin series is just a Taylor series centered at 0. It's just a special case. I don't know why it gets a separate name. I guess because somebody named Maclaurin invented it separately. So here's the definition of the Taylor series of a function centered at any number a. In class we'll look at some examples and see some uses of these. But for now, I'd like you to just bring this video question to class. Find the first three coefficients, C0, C1, and C2, for the Maclaurin series of the function sine x. Right, so that's the Taylor series centered at 0, like the first things we did. So we have formulas for C0 and C1 and C2. All you have to do is use this function and work out what those numbers are. Bring that to class, and I will see you there.